right, here we go with the washer method. So here we have a set up an integral representing a volume of revolution again. But in this case, we're saying, look at the area between two curves, y equals x squared and y equals the square root of x. Take that area and then revolve that about the x-axis, okay? So the first thing for me that I have to have in any one of these is I have to have a picture, all right? So how does this look? Well, I look at y equals x squared, so that's a parabola, so that's going to look something like this. All right, and then it's gonna go off this way, but I don't need to worry about that part because the square root of x is only in the first quadrant. Okay, so the square root of x is gonna look something like that. So here is y equals the square root of x, here is y equals x squared, and I don't really need this piece over here, okay? Because the area that I'm looking for is this area right there. Now, what I'm gonna do is I'm gonna notice that when I revolve this around that axis, I'm gonna get something that's gonna look something like this. So I'm going to have something along those lines. Okay, I'm doing my best to try and draw what this would look like as I spin this along the x-axis. Okay, so how does this work? Well, again, what I'm going to do is I'm going to take a little sample. Okay, I'm going to take a sample here, take a sample here, and I'm going to take that little wedge and just pop it out of the board. Okay, and what is that thing going to look like? So if I bring that over here, it's going to look something like this. If I tilt it to the side, it'll look something like this. Okay, so I've got my x-axis going through the middle, and now I have this hole. Okay, this hole is going to look something, I'm doing my best. Okay, something like that. That's why they call it a washer, because have you ever seen these little washers? Like, if you ever built something, they have like these little metal rings, right? But it looks like a metal circle, or it looks like a metal disc, but then there's a center part of it that's taken out. Okay, so there's like a hole in the middle of that disc. Okay, so that's exactly what this is saying. Now, what I notice is that this is delta x thick, okay? I'm taking a sample in the on the x-axis, so this is delta x thick. All right, so the first thing I need to understand is what in the world is the volume of a washer like this, okay? So the sample volume is going to be what? Well, let's think about this. It's going to be the area of this face, okay? So I got to miss the hole, so I got to miss that part. Okay, so it's going to be the area of that. Well, what in the world is the area of that face? Well, if this is the outer radius, so that's radius outer, okay, and I have this thing is the inner radius, r inner, well then I can say the area of the big disk with outer radius, I can take the area of that minus the area of the smaller disk. Okay, so what's that going to look like? That'll look like pi r outer squared minus pi r inner squared, and that's the area of the face, and to get the volume of this I need to multiply by how thick it is, so that's the delta x. Okay? Alright, so that's kind of cool, that's helpful. That's going to be a pi, I can factor that out, times radius outer squared minus radius inner squared times delta x. Alright, now the question is, well, what's the outer and what's the inner radius? So let's see, well, that's my center, so that's like my x-axis. The outer radius is from here out to the upper curve. So from here out to the upper curve. What's the upper curve? It's given by that. So radius outer is equal to the square root of x. And what's the inner curve? So that's going to be from here up to there, which is governed by y equals x squared. So r inner is equal to x squared. Okay, so I can now plug that in. So I'm going to end up getting pi times, okay, radius outer, we said was square root of x squared is just x, minus radius inner is x squared squared is x to the fourth, delta x. Fantastic. So that's telling me what my sample volume is of this particular thing. But now the question becomes, well, where do I integrate it from? Okay, well, I'm going to integrate it from the starting point out to this ending point, but the question is, what is that point? Well, that occurs when the two curves equal each other. And so if I set x squared equal to the square root of x, I get x squared equals the square root of x. And I say, well, when does that happen? Well, let's see. So if I square both sides, okay, I'm going to get x to the fourth equals x. So if I move that over, I get x to the fourth minus x equals 0. Okay, so I can take out an x. I'm left with x cubed minus 1 equals 0. Well, x cubed minus 1 vanishes at x equals 1, so I could factor this further as x times x minus 1 times stuff, okay? I mean, I know what this is, but you can work it out if you want, okay? You don't have to, but you can work that out. And I noticed that x squared plus x plus 1 has complex roots, so the only time this thing is equal to 0 is when x is 0 or x equals 1. So this is x equals 0 here, and that's x equals 1, and those are the bounds of my integral. So if my sample volume has this formula, then my actual volume will be the integral from 0 up to 1 of pi times x minus x to the 4th dx. Okay, so again, they just want you to set up the integral. This is a very simple power rule and fundamental theorem of calculus part 2. That's fine. The one thing that I do want to mention is that it is very important that you square your outer radius and then subtract the square of your inner radius. The number one mistake that people make is they do something like this, is they'll do like r outer minus r inner, and then they'll square the entire thing. Don't do that, okay? That's not following the geometric intuition for finding the area of this, what's called an annulus, but this is the area of the face of the washer, by taking the area of the larger disk minus the area of the smaller disk. So there you have it. There's the washer method. That's how you set up integrals for all of this. As always, like, subscribe, comment down below, share with your friends, and as always, these are my office hours. So please ask me questions and we'll keep it going.